Hello, this is chapter 9 of A Brief History of Time, and I am Akash. The Arrow of Time. The chapter 9 deals with how the time flows. Or does it flow, really? Or it is just a kind of illusion? In previous chapters, we have seen how our views of the nature of time have changed over the years. Up to the beginning of this century, people believed in an absolute time. That is, each event could be labeled by a number called time in a unique way, and all good clocks would agree on the time interval between two events. However, the discovery that the speed of light appeared the same to every observer, no matter how he was moving, led to the theory of relativity. And in that, one had to abandon the idea that there was a unique absolute time. Instead, each observer would have his own measure of time as recorded by a clock that he carried. Clocks carried by different observers would not necessarily agree, and thus time became a more personal concept relative to the observer who measured it. When one tried to unify gravity with quantum mechanics, one has to introduce the idea of imaginary time. Imaginary time is the indistinguishable from directions in space. If one can go north, one can turn around and head south. Equally, if one can go forward in imaginary time, one ought to be able to turn around and go backward. This means that there can be no important difference between the forward and backward directions of imaginary time. On the other hand, when one looks at real time, there is a big difference between the forward and backward directions, as we all know. Where does this difference between the past and the future come from? Why do we remember the past, but not the future? The laws of science do not distinguish between the past and the future. More precisely, as explained earlier, the laws of science are unchanged under the combination of operations or symmetries known as C, P, and T. C means changing particles for antiparticles. P means taking the mirror image so left and right are interchanged. And T means reversing the direction of motion of all particles. In effect, running the motion backward. The laws of science that govern the behavior of matter under all normal situations are unchanged under the combination of the two operations C and P on their own. In other words, life would be just the same for the inhabitants of another planet who were both mirror image of us and who were made of antimatter rather than matter. If the laws of science are unchanged by the combination of operations C and P and also by the combination C and P alone, yet there is a big difference between the forward and backward directions of real time in ordinary life. Imagine a cup of water falling off a table and breaking into pieces on the floor. If you take a film of this, you can easily tell whether it is being run forward or backward. If you run it backward, you will see the pieces suddenly gather themselves together off the floor and jump back to form a whole cup on the table. You can tell that the film is being run backward because this kind of behavior is never observed in ordinary life. If it were, crockery manufacturers would go out of business. The explanation that is usually given as to why we don't see broken cups gathering themselves together off the floor and jumping back onto the table is that it is forbidden by the second law of thermodynamics. This says that in any closed system, disorder or entropy always increases with time. In other words, it is a form of Murphy's law. Things always tend to go wrong. An intact cup on the table is a state of high order, but a broken cup on the floor is a disordered state. One can go readily from a cup on the table in the past to the broken cup on the floor in the future, but not the other way around. The increase of disorder or entropy with time is one example of what is called an arrow of time. something that distinguishes the past from the future, giving a direction to time. There aren't at least three different arrows of time. First, there is the thermodynamic arrow of time, the direction of time in which disorder or entropy increases. Then there is psychological arrow of time. This is the direction in which we feel time passes, the direction in which we remember the past but not future. Finally, there is the cosmological arrow of time. This is the direction of time in which the universe is expanding rather than contracting. In this chapter, I shall agree that no boundary conditions for the universe together with the weak entropic principle can explain why all three arrows point in the same direction, and moreover, why a well-defined arrow of time should exist at all. I shall agree that the psychological arrow is determined by the thermodynamic arrow, and that these two arrows necessarily always point in the same direction. If one assumes the no boundary condition for the universe, we shall see that there must be well-defined thermodynamic and cosmological arrows of time, but they will not point in the same direction for the whole history of the universe. However, I shall agree that it is only when they do point in the same direction that conditions are suitable for the development of intelligent beings who can ask the questions, why does disorder increase in the same direction of time as that in which the universe expands? However, I shall agree that it is only when they do point in the same direction that conditions are suitable for the development of intelligent beings who can ask the question, why does disorder increase in the same direction of time as that in... I shall discuss first the thermodynamic arrows of time. The second law of thermodynamics results from the fact that there are always many more disordered states than there are ordered ones. For example, consider a piece of a jigsaw in a box. There is one and only one arrangement in which the pieces make a complete picture. On the other hand, there are a very large number of arrangements in which the pieces are disordered and don't make a picture. Suppose a system starts out in one of the small number of ordered states. As time goes by, the system will evolve according to the laws of science and its state will change. At a later time, it is more probable that the system will be in a disordered state than in an ordered one, because there are more disordered states. Thus, disorder will tend to increase with time if the system obeys an initial condition of high order. Suppose the pieces of the jigsaw start off in a box, in the ordered arrangement in which they form a picture. If you shake the box, the pieces will take up another arrangement. This will probably be a disordered arrangement in which the pieces don't form a proper picture, simply because there are so many more disordered arrangements. Some groups of the pieces may still form a part of the picture, but the more you shake the box, the more likely it is that these groups will get broken up and the pieces will be in a completely jumbled state in which they don't form any sort of picture. So the disorder of the pieces will probably increase with time if the pieces obey the initial conditions that they start off in a combination of high order. Suppose, however, that God decided that the universe should finish up in a state of high order, but that it didn't matter what state it started in. At early times, the universe would probably be in a disordered state. This would mean that disorder would decrease with time. You would see broken cups gathering themselves together and jumping back onto the table. However, any human being who were observing the cup would be living in a universe in which disorder decreases with time. I shall argue that such beings would have a psychological arrow of time that was backwards. That is, they would remember event in the future and not remember events in their past. When the cup was broken, they would remember it being on the table, but when it was on the table, they would not remember it being on the floor. It is rather difficult to talk about human memory because we don't know how the brain works in detail. We do, however, know all about how computer memories work. I shall therefore discuss the psychological error of time for computers. I think it is reasonable to assume that the error for computer is the same as that for humans. If it were not, one could not make a killing on the stock exchange by having a computer that would remember tomorrow's price. A computer memory is basically a device containing elements that can exist in either of two states. A simple example is an abacus. In its simplest form, this consists of a number of wires. On each wire is a bead that can be put in one of the two positions. Before an item is recorded in a computer's memory, the memory is in a disordered state with equal probabilities for the two possible states. The abacus beads are scattered randomly on the wires of the abacus. After the memory interacts with the system to be remembered, it will definitely be in one state or the other, according to the state of system. Each abacus bead will be at either the left or the right of the abacus wire. So the memory has passed from a disordered state on an ordered one. However, in order to make sure that the memory is in the right state, it is necessary to use a certain amount of energy to move the bead or to power the computer, for example. And this energy is dissipated as heat and increases the amount of disorder in the universe. One can show that this increase in disorder is always greater than the increase in the order of the memory itself. Thus, the heat expelled by the computer cooling fans means that when a computer records an item in memory, the total amount of disorder in the universe still goes up. The direction of time in which a computer remembers the past is the same as that in which disorder increases. Our subjective sense of the direction of time, the psychological error of time, is therefore determined within our brain by the thermodynamic arrow of time. Just as a computer, we must remember things in the order in which entropy increases. This makes the second law of thermodynamics almost trivial. Disorder increases with time because we measure time in the direction in which disorder increases. You can't have a safer bet than that. But why should the thermodynamic arrow of time exist at all? Or, in other words, why should the universe be in a state of high order at one end of the time, the end that we call the past? Why is it not in the state of complete disorder at all times? After times, this might seem more probable. And why is the direction of time in which disorder increases the same as that in which the universe expands? In the classical theory of general relativity, one cannot predict how the universe would have begun because all the known laws of science would have broken down at the Big Bang singularity. The universe could have started out in a very smooth and ordered state. This would have led to the well-defined thermodynamic and cosmological arrows of time, as we observe. But it could equally well have started out in a very lumpy and disordered state. In that case, the universe would already be in a state of complete disorder. So, disorder could not increase with time. It would either stay constant, in which case there would be no well-defined thermodynamic arrows of time, or it would decrease, in which case the thermodynamic arrow of time would point in the opposite direction to the cosmological arrow. Neither of these possibilities agrees with what we observe. However, we have seen classical general relativity predicts its own downfall. When the curvature of space-time becomes large, quantum gravitational effects will become important and the classical theory will cease to be a good description of the universe. One has to use a quantum theory of gravity to understand how the universe began. In a quantum theory of gravity, we saw in the last chapter, in order to specify the state of the universe, one would still have to say how the possible histories of the universe would behave at the boundary of the space-time in the past. One could avoid this difficulty of having to describe what we do not and cannot know only if the histories satisfy the no-boundary conditions. They are finite in extent, but have no boundaries, edges, or singularities. In that case, the beginning of the time would be a singular. In that case, the beginning of time would be a regular, smooth point of space-time, and the universe would have begun its expansion in a very smooth and ordered state. It could not have been completely uniform, because that would violate the uncertainty principles of quantum theory. There had to be small fluctuations in the density and velocities of particles. The no-boundary conditions, however, implied that these fluctuations were as small as they could be, consistent with the uncertainty principle. Thank you very much for watching. See you in the next part of the chapter, The Arrow of Time.